All right, so we have been doing things related to random variable estimation, and then we follow that with some discussion that is related to linear regression and how to handle linear regression. For the random variable estimation, we discussed it in the linear case, in the generalized case, and every single time the solution did involve just the derivative. You just need to know what you are making a derivative for and just work on the setup of your problem appropriately. But, I mean, if that is the case, why can't we just like differentiate everything? Every single problem we have, differentiate, and that's it. Why is there even some science called optimization? Just differentiate. Go to the first lecture, tell them differentiate, goodbye, and then leave. Problem solved. Because in real life, pretty much every single optimization problem has what is so-called constraints. Optimization problems are not open. Optimization problems are restricted. There are certain constraints you need to fulfill such that you can handle or generate a feasible solution for an optimization problem. Let's give two examples. If you are just like having a limited number of objects and you want to distribute the objects into different pots in order to achieve certain goal. So you are optimizing on the fraction of the objects you have, you will put in every single pot. What is the obvious constraint in this problem? Fractions, right? So, like probabilities, right? You cannot have an outside object and put it so. They should sum to 1, right? So the total, the sum of all these fractions should sum to 1. It's just a fraction of what you have, right? In a wireless communication problem, I mean, why can't you just like send infinite energy and then your system will be extremely reliable and everybody's happy? Why can't you do that? Because you always have energy constraints, right? There are people who spend their entire lives working on the optimization of energy systems, right? So every single optimization problem in real life has constraints. So handling an optimization problem with constraints is what we will talk about starting from this lecture and until the end of the first module. And this science is called, in part called convex optimization. Obviously, there are many problems that are non-convex, but at least the problems we will mainly discuss are convex problems, all right? We will start off with the simplest version of these problems, which is the linear programming problem. So what is the problem here? Constraint optimization of a linear function. And the problem formulation is minimize C transpose X subject to AX less than or equal to B. Is C transpose X a scalar or a vector? Yeah, right? So this is a scalar, and it is called the objective function. And this is called the constraint region. You could easily anticipate that this constraint region is going to be what? Every single line of this inequality, every single line, so line here means literally line of an inequality, row of an inequality. It actually refers to a line, right? So you could easily anticipate that this is going to be just a region like this. A bunch of lines in a multi-dimensional space, and then you are looking inside them. All right? Immediate question. If we don't have a constraint, what is the optimal solution for this? What's up? Raise your voice. Okay, so the same thing happened yesterday. Why do you assume this cannot be negative? Your logic is correct, but why cannot be negative? So the answer is minus infinity, right? So let's assume the simple case of your coefficients being all positive. You could always put all your x's to minus infinity, minus infinity, minus infinity, and get this thing to minus infinity. Let's assume they are all negative. You could always put them to infinity, 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 and such that they sum to minus infinity. So the solution of the unconstrained version of this is just minus infinity. You can get to minus infinity. It's just a line, right? But obviously, this will never happen because you have a constraint, all right? Let's look at an example to materialize this more. So example 1. In this example, we have this optimization problem, minimize C transpose X, subject to AX less than or equal to B. And here you have C and X, both C and X, belonging to R2 by 1. A belongs to R5 by 2. B belongs to R5 by 1. And the constrained region is shown. Let's call it CR. And finally, or RC, like region constraint, it really doesn't matter. And finally, we want to suggest where X star could be. So this is our constraint region. It looks like this, 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 and this. First of all, before discussing any mathematics, is this notation clear? Anybody's confused about this notation? How many of you are fine with this notation? It's just a vector, right? So there's no problem. So this is a vector, 2 by 1, this is a matrix 5 by 2, this is a matrix 5 by 2, and they are all real, okay? All right, so let's try to think about the solution of this problem. We can write our objective function. We can call it f0 of x as C transpose x equals C1 x1 plus C2 x2 equals A. How does that thing look like? What is this? C1 x1 plus C2 x2 equals A. What is this? A line, absolutely. So let's assume some line. Let's assume some line like this. No, that is not a good line. Like this. What happens when we play with the value of A? Increase it or decrease it. What happens to this line? When we increase or decrease A, what happens to this line? Obviously, this is assuming a specific value of A, right? For example, if it is 0, the line has to pass by the origin. When we increase or decrease the value of A, what happens to this line? You move the line. Good. The line moves with respect to the one we have already drawn for a specific A. Those lines, the moving lines, will look like what? Orthogonal, parallel, how would they look like? Exactly, right? So when you play with the value of A, you get some lines like this or this. All right? We can assume that the direction of decreasing A is something like this. That is the direction of decreasing A. You are moving here, you are decreasing A. Based on this assumption, can someone suggest where X star should be? And someone needs to answer this. Can someone suggest a point? Go ahead.
So it needs to be within the region.
It has to, right?
So the upper corner of the...
Yeah. Did you understand her answer? So it has to be within the region. You keep moving in the direction of decrease until you hit a corner. There is one little thing missing here, which is we just assumed the line and assumed its direction of decreasing. So what is the general answer of this? The solution. Exactly. So X star has to be at one of the 5 corners. Even though I don't like people memorizing things, but this is something that is cool to memorize and can make your life very easy. The solution of any linear programming problem is guaranteed to be at one of the corners of the region. Is guaranteed to be at one of the corners of the constraint region. Just one what? Yeah, one of them, yeah. It depends on your line and whether it is the direction of increase or decrease is this way or that way. For example, here, if that was the direction of decrease, as she said, the solution will be here. If that was the direction of decrease, you will keep moving, and it depends on whether you will meet this one last or this one last. Yeah.
If we take our line to be parallel,
You are spoiling my question. It's a very good question, I'm just joking. But you are spoiling my next question, literally. So that's my next question. So Q, first of all, thank you very much. So when is the solution any point on an entire line? You answered it already, so. But can someone else also answer in addition to her? When is the solution is any point on an entire line? The 2 corners and any point on the line. All right. Yeah. So she already answered it and you completed the answer. So if you have your line being parallel line to that side. For example, if this guy was tweaked like this, such that it is parallel to this line, it keeps moving until it hits the entire line. When it hits the entire line, every single point on this line will be an optimal point. So it is guaranteed to be at the corners, but in addition to that, if you are parallel to one of the sides and the direction of increase is orthogonal to both of you, you will also hit an entire line of optimality. All right? That is the linear programming problem. Now, let's move on to convex and concave functions. So a function f of x is convex over the interval from a to b if for every x1, x2 that belongs to A and B, and lambda in 0 to 1, this relation holds f of lambda x1 plus 1 minus lambda x2 less than or equal to lambda f of x1 plus 1 minus lambda f of x2. That is for convexity. And for concavity, we have f of lambda x1 plus 1 minus lambda x2 greater than or equal to lambda f of x1 plus 1 minus lambda f of x2. So, first of all, how many of you have heard these terms, convexity and concavity, before? Few people. How many of you have seen this definition strictly before? Okay, almost no one. All right, so let's try to illustrate this through examples. Well, yeah, assuming that the marker is operating. We have this function, and then we have this function, that is f of x with x, f of x with x, x1, x2, x1, x2, f of x1, f of x2, f of x1, f of x2. And then we have here a point and another point. And here we have a point and another point. All right. So this definition is saying that a function f of x is convex over ab for every x1 and x2 if the function is less than or equal to the linear combination of functions. It is concave if the function of the linear combination is greater than the linear combination of functions. So just to remember these terms, so convex, for anybody who is wearing glasses like myself, it is the standard thing, so you have an idea about convexity, right? Concavity, you could think about it in terms of the name as a cave. So convex for glasses, concave for caves. There is one trivial childish interpretation. It's like sad, this childish, forget about it. Anyways, let's look at these two things. If we call this term 1 and we call this term 2, and we look at the left graph, is this 1 or this is 1? Where is 1? 1 is up or down? Down, thank you. So this is 1 and this is 2. Here it is the opposite. This is 1 and this is 2. So this is the function of the linear combination, and this is the function of the linear combination. This is the linear combination of functions and the linear combination of functions. Here, the function is less. Here, the function is more. All right? You could try to connect the dots until we get there. You could easily see that these functions, their optimization is going to be easier than functions that has local minima and local maxima, right? So that's why we will focus on these primarily in the rest of the course, in the rest of the module, if we can say. All right. Some theorem that is quite useful that we have if fi of x I equals 1, 2, ... to n are convex or concave, then g of x, which is summation from I equals 1 to n ci fi of x, is also ci greater than or equal to 0, is also convex concave. So the linear combination of functions where your coefficients are greater than or equal to 0, if your functions are convex, the linear combination is convex. If they are concave, the linear combination is concave. Do we really need to prove that? You just literally plug in this. Literally, there is nothing, I mean, it's just that you replace this x by lambda x1 plus 1 minus lambda x2 equals summation from I equals 1 to n ci fi of lambda x1 plus 1 minus lambda x2. And then you use the individual convexity, concavity, problem solved. All right? Good. So, multiple useful points to remember. So, if second derivative of f non-negative, if second derivative of f non-positive, do you think for the first case it will be convex or concave? Convex, absolutely. Thank you. And for the second one, it will be concave. All right. Another point that is also important, which is if f is convex minus f is concave. Lastly, if f is linear. If f is linear, what is this? Will it be convex or concave? Both or neither?
I think both because this message said non-negative derivative.
Yeah, thank you so much. And this non-negative, it comes from the non-strict equalities here. You have the equality with you as well. So if f is linear, as many of you said, it is both convex and concave. What you said is correct if we said whether they are strictly convex, concave, or not. All right? So if f is linear, which is also called affine, I don't really know why should we use another name if linear is already good, but yeah, they always say that. So when you see this affine thing, you should know it means linear as well. So if f is linear, it means it is convex and concave at the same time. All right? Let's do some quick examples. Example 2, test convexity, concavity for two functions. A, f of x equals x squared. B, f of x equals ln x. What is the quickest way of handling these? Second derivative. Yeah. 2 steps quickly, everything is done. F prime of x equals 2x. F double prime of x equals 2. Strictly positive, convex. And f prime of x equals 1 over x. F double prime of x is minus 1 over x squared less than 0 on the domain x greater than 0, concave. So the log, which is a very important function, looks like this, and it is a concave function. All right? Everybody's okay? So everything we have discussed about convexity and concavity, we can now go on and do a little trick to make our life easy instead of writing again. It applies also to the case of having all of these being points in n-dimensional spaces rather than just points on a line. All right? Which is the more interesting case, obviously. It's just that, yeah, discussing it in terms of points on a line is much easier. Okay? All right. The hardest part of this module and the hardest part of today's lectures is starting. Possibly even the hardest in the whole course. duality in optimization. So we have an optimization problem, and that is its standard form. And it is minimize f0 of x subject to fi of x less than or equal to 0, I1 to m, hi of x equals 0, I1 to p. And we have the variable x is in Rn. That's our optimization variable. Its domain is D. So that is the domain in which a solution is feasible. And f0 of x star, the optimal, is p star. So this is a generic form of an optimization problem. You want to minimize an objective function subject to a bunch of constraints. Here we have two types of constraints. The first type is fi of your vector x less than or equal to 0, multiple functions. hi of x equals 0, multiple functions, is the second type of constraint. Is that clear until now? Okay. In duality, we will create a dual problem. A problem that is not strictly this problem, but it has all the ingredients of this problem. A question that we have already answered implicitly: why can't we solve this problem immediately by differentiation, by gradients? Why? Because of this. This is a long process that we will try to go on together until Thursday. So from now until Thursday, all that we will be trying to do is to build another problem, another optimization problem. The other optimization problem, in nature, it's a function that bounds this p star from below. It's a lower bound for the optimal we are seeking. And then, since it is a bound from below, we will try to maximize it to get to p star. That is the vision of what we will be doing from now until almost the end of the module. So we will get to another function that bounds p star from below, if that is p star, and we will try to maximize this function until we get to p star. Okay? So the first step in doing this is we will create something called the Lagrangian. What is this Lagrangian? It is L of x, lambda, and mu, which is f0 of x plus summation from I equals 1 to m lambda I fi of x plus summation from I equals 1 to p nu I hi of x. Fundamentally, what is this? This is just a weighted sum of the objective function and the constraint functions. So you could see that there is relation, and you could see intuitively that, oh, in the past we had an optimization problem where we had a function, the objective function doesn't include the constraints in it. We took a step possibly in the right direction by having a function with the constraints all together in one place, called the Lagrangian. All right? So this is weighted sum of the objective and the constraint functions. And then we will create a function that is g of lambda and mu, which is the infimum over x, L of x, lambda, and mu. Before you ask, anybody is familiar with this term infimum? What does infimum mean? Infimum means the greatest lower bound. Let's give a quick example here. If you have a set S that is x such that x greater than square root 2, so this is your value square root 2. The value square root 2 doesn't belong to the set. This is the set, right? You could bound the set from below by anything. You could have even a lower bound as stupid as minus infinity. It's a lower bound for everything. Yeah, zero entropy information, but okay. The greatest lower bound, the greatest that you cannot have a lower bound greater than it is the square root 2 itself. So x equals square root 2, or let's say z equals square root 2 is the infimum of S.
So what was the name of the opposite one?
Supremum. And it is the lowest upper bound. All right? But you see the other one in many limits when they do lim sup, because the limit itself doesn't exist, so they limit the supremum of it. But probably you ignore it, assume it's a limit and you don't care. I used to do that too. All right. So, until now, do you have any questions? Let's try to take this a step further and think of some relation between this G of lambda and nu with F0 of x star equals P star. Without looking at the notes, can someone tell me what is the relation between these two and 1? Equal, smaller, greater. All right. When you substitute here x equals x star, let's do it step by step. When you substitute here x equals x star, what happens to this term? What happens to this term for any feasible x, actually? Yeah, of course. From the constraint, this is gone. So we only have these two remaining. When you do this infimum on this, how could you relate it to this one alone, f0 of x star? Is it greater or less? Now it all depends on this one, right? On this term. Based on this term, what do you think? Because there is one condition missing, which is essentially that lambda I greater than or equal to 0 for all I. Now, does that help you answer the question? The lambdas are positive. This term is strictly, thank you so much, this term is strictly negative, and thus this is a lower bound on P star. Good, I took a step further. Now we created this function, the Lagrangian, we got its infimum to cancel x out, and we got some lower bound on the optimal value we are seeking. One question, even you can answer it intuitively and we can see it through examples. This G is convex or concave in lambda mu, this G, this infimum thing. Should it be like this or like that? It's that you are thinking about what is the best you could do, but you shouldn't. You should think about it's an infimum problem. So for an infimum problem, yeah. So it will end up being a concave function of lambda mu. So concave in lambda and mu. That is why you will need later on to maximize it, right? If it is convex, it goes to infinity and it crosses your P star anyways, right? All right? So this is a concave function in lambda and mu. One last time before we do two examples to illustrate what is happening. We had a standard optimization problem, minimization of objective function with a bunch of constraints. The bunch of constraints are preventing us from just taking some gradient. And based on that, we invented some Lagrangian function that is not particularly an invention. It is just the objective function and a weighted sum of the constraint functions. And then we have demonstrated that the infimum over x of this, which is g of lambda and mu, gives us some lower bound on the value we are seeking, P star. That's what we did from the beginning until now. The next step, which is not something we will do today, we will do next time, is we will try to get to this maximum of g of lambda and mu such that we get as close as possible to P star. And this maximization problem is what we will call next time the dual problem. It's a dual optimization problem. Dual to what? Dual to the standard form problem. All right? So in that case, this one will be called the primal. This one will be called the dual. All right. In the remaining part of the lecture, we will just do two examples. So let's assume that you have this optimization problem. Minimize x transpose x subject to ax equals b. And here in particular, we don't want to take this problem until the end. The only thing we want to do is to get the g and to think about the g, to discuss it. Can someone help me with the Lagrangian? First of all, the Lagrangian is function of x and what? Yeah, it is x lambda mu. That's what's written here. Are there lambdas here? Who's talking? Yeah, there are no lambdas here, right? So this thing is only function of x and mu because we only have equality constraints, so we only have these. Right? There are no inequality constraints here. So L of x and nu is x transpose x plus nu transpose ax minus b. You got to write the constraint on the standard form, so it's ax minus b equals 0. All right? This would be like your h's, right? And since they are a bunch of linear equations, you can write it as mu transpose ax minus b. All right? Any problems until now? Okay. So we want to get the infimum of this. So we will get the gradient of L, x, and nu. What is the gradient of this first term? 2x, we just did it together, 2x. This term is a constant, will go away. What is the gradient of this term? Nu transpose ax. Yeah, with just a little tweak that you need to take care of when you do these things, that nu transpose A is a row vector. This is a row vector. It got to be a column vector, right? So actually, when you do the calculations, it will literally end up being this thing transpose. So your answer is correct, but in the transpose form, all right? So this is 2x plus A nu transpose. So to minimize or to get the infimum of L, x, and nu on x, x has to be minus 1/2 A nu transpose. So g of nu is L of minus 1/2 A nu transpose and nu. Just make some direct substitution here. You will get minus 1/4 nu transpose A transpose nu minus nu transpose B. All right. Is this thing convex or concave? We know it's concave from the beginning, but can someone tell me why is this thing concave? Think about it in the scalar version. So the scalar version of this is minus 1/4 nu squared a squared, right? And some linear thing. So the order of this function is in terms of the minus nu squared, right? Minus nu squared is concave, right? Clear to everybody? So this function is concave in nu. And we already know that from the beginning, this is going to be less than or equal to p star. All right, let's do another thing, which is the linear programming problem. Let's revisit the problem again without geometric interpretation. So we want to minimize C transpose X subject to AX equals B and xi greater than or equal to 0 for all I. Can someone help me once again with the Lagrangian? You have everything, right? You have lambdas, you have nus. You have inequality constraints, you have equality constraints. So L of x, lambda and nu is C transpose X. Then what? We can use the same trick we used here, right? Can use the same trick we used here. So this xi greater than or equal to 0 itself, it can be written as the vector notation x greater than or equal to 0, where if you have x greater than or equal to y, this means xi greater than or equal to yi for all I. So we can write the constraint this way. Okay, we did the first step. What is the second step? What is the term that will be function of lambda here?
Could you please repeat the question?
So I want the term that will be function of lambda. So here we had a term function of x, term function of mu. The term function of mu here is trivial. It's the same term we just did. The only remaining term is the term function of lambda. What is that term? Minus 1. It's function of lambda. Right? First of all, why do you say minus?
Because it has to be correlate for all I, if I should lower than the 0.
Yeah.
Therefore, we should convert it by minus. And lambda vector must be all minus 1, I think.
So you have said two things. The first of them is perfect. So first of all, it is very important to look at your constraint. The constraint is less than or equal to. Here we have it greater than or equal to. What he is saying is, no, this doesn't work. We got to make it like this. And this is perfectly correct. But the only problem you had in the second part is that you tried to jump on the values of lambda. But the lambdas will stay the same. The lambdas will stay the same, but your logic is perfectly correct, and it will be minus lambda transpose x instead of the ones you had. But this minus thing, this is, yeah, thank you. This is tricky. It got to be minus lambda transpose x, all right? Well, this is quite important. And then the last term we have seen before, there is not anything complicated about it. Mu transpose ax minus b. So we can rewrite this thing as minus b transpose mu plus c plus a transpose mu minus lambda over all transpose x. Remember that this is a scalar. So this is a scalar, mu transpose b, b transpose mu. This is a scalar, it doesn't matter. Okay. without any optimization or anything, because it's quite obvious that when you try to optimize this to get any gradient, the x will go away. So the gradient here is not going to help you at all, right? What do you think of the infimum of this cell? What do you think this g of lambda and mu, which is the infimum over x, L of x, lambda, and mu, will be? Great. So it is. We have two branches. One branch, you got it right, minus infinity otherwise. Just a linear function of x. You can keep picking x that give you minus infinity. No problem about that, right? Yeah. Yeah. Do you understand what she's saying? She said that you can do that as long as this guy is not 0. If it is 0, the term having x will go away anyways, right? So when this is actually happening, this becomes minus p transpose mu for the case of C plus A transpose nu equals lambda. All right? Is this function a concave function? Yeah, it is a linear function, so it's convex and concave and everything you want. And you could also see that it's the same thing. This particular value is going to be, both of them actually, but this one is like a zero entropy bound. It's the minus infinity anyways, so this will also be less than or equal to p star. Next time we will talk about the dual problem, and we will dig deep into this convex optimization, and we will talk about the gradient descent algorithm. All right? See you on Thursday.